The quest to create intelligent machines has captivated humanity for centuries. From the earliest days of civilization, humans have been fascinated by the idea of creating entities that could think and act like us. This fascination is evident in the myths and legends passed down through generations. Myths and stories explored the idea of artificial beings with human-like intelligence. Ancient cultures imagined golems, automatons, and other mechanical beings brought to life through mystical means. These stories laid the groundwork for our modern understanding of artificial intelligence. Today, this ambition is no longer confined to the realm of fiction. The rapid advancements in technology have turned these age-old dreams into a burgeoning reality. Scientists and engineers are working tirelessly to push the boundaries of what machines can do. Artificial intelligence, or AI, is rapidly transitioning from a futuristic concept to a tangible reality. We see AI in our daily lives, from virtual assistants on our phones to recommendation algorithms on our favorite streaming services. This transformative technology is poised to reshape industries, redefine our relationship with machines, and fundamentally alter the fabric of society. In factories, robots are taking on tasks that were once dangerous or monotonous for humans. In healthcare, AI is helping doctors diagnose diseases with unprecedented accuracy. The rapid advancements in AI can be attributed to several factors. One of the most significant is the exponential growth in computing power. Modern processors can perform complex calculations at incredible speeds, enabling AI algorithms to process vast amounts of data. The exponential growth in computing power, coupled with the availability of massive datasets, has provided fertile ground for AI algorithms to flourish. Data centers around the world store and process information on a scale that was unimaginable just a few decades ago. Moreover, breakthroughs in areas such as machine learning and deep learning have enabled machines to learn from data and perform complex tasks that were once thought to be the exclusive domain of humans. Neural networks, inspired by the human brain, allow AI systems to recognize patterns and make decisions with remarkable accuracy. As AI becomes increasingly integrated into our lives, it is crucial to develop a foundational understanding of its core concepts, its far-reaching implications, and its potential to shape the future. Educational institutions are now offering courses on AI, preparing the next generation to navigate this rapidly evolving landscape. This essay delves into the exciting world of AI, exploring its various facets, from the fundamental principles that underpin its existence to the philosophical questions it raises about the very nature of intelligence and consciousness. As we stand on the brink of a new era, it is essential to consider not only the technological advancements, but also the ethical and societal implications of creating machines that can think and learn. Defining artificial intelligence is akin to defining intelligence itself, a concept that has puzzled philosophers and scientists for centuries. At its core, AI endeavors to create machines capable of performing tasks that typically require human intelligence. This includes a wide range of cognitive abilities, such as learning, reasoning, problem-solving, perception, and natural language understanding. However, AI is not merely about replicating human intelligence. It also encompasses the development of systems that surpass human capabilities in specific domains. For instance, AI systems can analyze vast amounts of data, identify patterns, and make predictions with a speed and accuracy that far exceeds human capacity. This ability to process information and extract insights has made AI an invaluable tool in various fields, from finance and healthcare to transportation and entertainment. Despite significant progress in the field, true artificial general intelligence, or AGI, AI that possesses the same cognitive abilities as a human being, remains elusive. Current AI systems excel in specific tasks but lack the general intelligence and adaptability that characterize human cognition. Nevertheless, the pursuit of AGI continues to drive research and innovation in the field, pushing the boundaries of what machines can achieve. Machine learning, or ML, is a subfield of AI that focuses on enabling machines to learn from data without being explicitly programmed. This means that instead of following a set of predefined instructions, the machine uses algorithms to identify patterns and make decisions based on the data it receives. Instead of relying on predefined rules, ML algorithms learn patterns and relationships from data, allowing them to make predictions or decisions based on new, unseen data. This process involves training the algorithm on a dataset, which helps it to understand the underlying structure and relationships within the data. This ability to learn from experience is a fundamental aspect of human intelligence and a driving force behind the recent surge in AI applications. By mimicking this human trait, machine learning systems can adapt to new information and improve their performance over time, making them incredibly powerful tools in various fields. There are three main types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Each type has its own unique approach to learning from data and is suited to different kinds of tasks and problems. In supervised learning, algorithms are trained on labeled data, meaning the input data is paired with the desired output. This type of learning is akin to a student learning from a teacher, where the correct answers are provided during the training process. The algorithm learns to map inputs to outputs, enabling it to predict outputs for new, unlabeled data. This is particularly useful in applications such as image recognition, where the algorithm can identify objects in new images based on its training. Unsupervised learning, on the other hand, deals with unlabeled data. Here, the algorithm is not given any explicit instructions on what to look for. Instead, it must find patterns and structures in the data on its own. Algorithms are tasked with finding patterns and structures in the data without any prior knowledge of the desired output. This type of learning is often used for clustering and association tasks, where the goal is to group similar data points together or identify relationships between variables. Reinforcement learning involves training agents to make decisions in an environment to maximize a reward signal. This type of learning is inspired by behavioral psychology, where agents learn to achieve their goals through trial and error. The agent learns through trial and error, receiving positive reinforcement for desirable actions and negative reinforcement for undesirable ones. This approach is particularly effective in dynamic environments where the optimal strategy is not immediately obvious. Machine learning has found widespread applications in various domains. Its ability to analyze vast amounts of data and extract meaningful insights has revolutionized many industries. In healthcare, ML algorithms analyze medical images to detect diseases, predict patient outcomes, and personalize treatment plans. This has led to significant improvements in diagnostic accuracy and patient care. In finance, ML powers fraud detection systems, risk assessment models, and algorithmic trading platforms. These applications help financial institutions manage risk, detect fraudulent activities, and optimize trading strategies. The ability of ML to extract meaningful insights from vast amounts of data has made it an indispensable tool for businesses and organizations across industries. From improving customer experiences to optimizing supply chains, machine learning is driving innovation and efficiency in countless ways. Deep learning, or DL, is a specialized area within machine learning that employs artificial neural networks with multiple layers to analyze complex data. These networks are designed to mimic the way the human brain processes information, allowing them to identify patterns and make decisions with a high degree of accuracy. By leveraging vast amounts of data, deep learning models can learn to perform tasks that were previously thought to be the exclusive domain of human intelligence. Inspired by the structure and function of the human brain, artificial neural networks consist of interconnected nodes or neurons organized in layers. These layers work together to process input data, with each neuron performing a small part of the overall computation. The architecture of these networks allows them to handle complex tasks by breaking them down into simpler, more manageable components. Each connection between neurons has a weight associated with it, which determines the strength of the connection. These weights are adjusted during the training process, allowing the network to learn from the data it is given. By fine-tuning these weights, the network can improve its performance on specific tasks, making it more accurate and efficient over time. The depth in deep learning refers to the number of hidden layers in the neural network. These hidden layers are crucial for the network's ability to learn complex patterns and representations. The more layers a network has, the more abstract and high-level features it can extract from the data. This depth is what gives deep learning its power and flexibility. These hidden layers allow deep learning models to learn hierarchical representations of data, extracting increasingly abstract features as data flows through the network. This hierarchical learning process enables the network to build a more comprehensive understanding of the data, making it capable of performing tasks that require a high level of cognitive ability. This ability to learn complex patterns and representations has made deep learning particularly successful in areas such as image recognition, natural language processing, and speech recognition. In image recognition, for example, deep learning models can identify objects and scenes with remarkable accuracy. In natural language processing, they can understand and generate human language, enabling applications like chatbots and translation services. In speech recognition, they can transcribe spoken words into text with high precision. One of the key advantages of deep learning is its ability to automatically learn features from raw data, reducing the need for manual feature engineering. This automation allows for faster development and deployment of AI models, as it eliminates the time-consuming process of manually selecting and extracting features. Additionally, it enables the models to adapt to new data and tasks more easily, making them more versatile and robust. For instance, in image recognition, deep learning models can learn to identify edges, corners, and other low-level features in the early layers of the network. These low-level features are the building blocks for more complex patterns, and their accurate identification is crucial for the overall performance of the model. Gradually, as the data passes through the deeper layers, the network begins to recognize more complex features, such as shapes and objects. This progression from simple to complex feature extraction allows the network to build a detailed and nuanced understanding of the data, enabling it to perform tasks with a high degree of accuracy and reliability. This hierarchical feature learning allows deep learning models to achieve state-of-the-art performance on a wide range of tasks. From medical diagnosis to autonomous driving, deep learning is revolutionizing various fields by providing solutions that are both innovative and effective. The continuous advancements in this technology promise to unlock even more complex patterns and applications in the future, pushing the boundaries of what artificial intelligence can achieve.